Okay, hello everyone. My name is Ichai. I'm a PhD student from Center of Solar Terrestrial Research at NJIT. Today I'm going to present study of sunspot 3-minute oscillation using these two instruments, ALMA and GST. So in my talk, I'm going to cover the following materials. Basically, the first one is quite obvious. There's the sense motivation of the problem. Well, what is a sunspot oscillation, and why do we study it? And then I will touch into some of the features, the advantage of using ALMA in the solar observations, and then I will come to the observations of this specific sunspot, AL12470, followed by the analysis, discussion, and the conclusion. But first, since most of you are not familiar with the observing the sun using ALMA, so I want to first show the millimeter sun, basically the sun observed using ALMA. So here to the right, this figure shows the full disk map of the sun observing using several instruments, including ALMA, that's basically the top two panels, as well as AIA, the bottom left, and HMI image, that's the bottom right. So keep in mind, these two are the full disk image of the sun. So they're not in a fine resolution. Here, you can see I marked with these 4 squares. Basically, this one shows the field view of the interferometer image from ALMA, which is showing on the left figure. So in this left figure, basically we have the interferometer image of ALMA band 3 with the H alpha image from the BBSO GST as a comparison. So I want to point out that the ALMA images are taken in a snapshot mode for this particular observation, so that we can actually show a movie that have the dynamics in the sunspot. Let me show you if I can play this. So you can see as the movie goes, we see the feature, and it's actually oscillation appears in this sunspot region. And this dashed line marks the field of view in this Big Bear solar observatory H alpha image. And I want to point out this one is a movie that have a time interval between each frame is 2 seconds in the original image, and the whole period is about 10 minutes, as it's the whole scan duration of one particular on-target time. So let me get into the point. What is a sunspot oscillation, and why do we study them? So basically, sunspot oscillations are frequently studied with phenomenon in the solar atmosphere. And there are 2 types of characteristic oscillations in the sunspot. For the first 5-minute oscillation driven by the pressure mode, P mode, that's the pressure wave, and also the 3-minute oscillations representing the resonant mode of the sunspot itself. So the study of sunspot oscillation ties in with several other areas of research, since these oscillations are directly connected with the propagation of solar amplitude waves. It can serve as a probe of the structure of the solar atmosphere. And it also figures prominently in the variety series of the wave heating of the upper solar atmosphere, giving it an important role in solving the coronal heating problem, which is actually can be seen on this figure. So this figure shows a temperature versus as a function of height of the solar atmosphere. You can see we have a huge jump from this chromosphere to the corona in this transition region. And it is believed that the sunspot oscillation is highly related with this energy releasing process. So definitely it's a quite interesting object to study. So that actually leads to the advantage of using ALMA to observe the sun. First thing is that its frequencies arise from different heights in the chromosphere, which is actually represented by this figure showing the contribution function of the continuum intensity at for selected wavelengths. So basically, you can see we have quite identical wavelengths that can see different layers in the chromosphere where the oscillation happens, and this is the most interesting region. And the radiation in millimeter and sub-millimeter is mainly formed through free emission in the chromosphere, so the source function is Planck-like, and the region's approximation can be applied, which leads to the linear relationship between ALMA brightness and the plasma temperature. And it makes ALMA a unique instrument in providing directly electron temperature measurement at varying heights in this chromosphere, just like this figure shows. So another advantage is of ALMA observation and its spatial and temporal resolution. This figure I'm showing here is a specific target of ALMA solar convention campaign data taken on December 17th, 2015. Each of the solar scan is about 10 minutes, marked with T1 to T5, with a cadence of 2 seconds. And this is perfect to resolve the 3-minute period typical of sunspot oscillation in the chromosphere. So with these advantages, basically, ALMA become a nice tool to study the sunspot oscillation. Okay, let me come to the observation of this specific sunspot AR12470. So basically, we analyze the oscillation signal measured in the west part of this active region during a 1-hour observation period, which was a part of ALMA solar convention campaign. The observation was conducted using band 3 centered at 100 GHz. And due to the necessity of phase calibration, we have this block on target observations were run for about 10 minutes of a cadence of 2 seconds, followed by 220 seconds of target phase calibration. So that's why you can see all these gaps. Basically, these are the phase calibration necessary for the unsolar observations. We also apply the self-calibration method so that we can counter the phase error introduced by the Earth's atmosphere. Okay, so let's go to the analysis. So you visualize this oscillation motion in the sunspot. We made several time distance plots along the line that cross both the umbra and penumbra. You can see here in this bottom right corner. So this double solid line in this panel marks the width of the slit for which the data are summed. Immediately, you can see we have this chevron shape in several of the wavelengths from different instruments. These appear first in the center of the umbra and then propagate to the edge. So the 3 minutes oscillation motion in these panels also extend somehow into the penumbra. You can see that's the mark with the umbra penumbra boundary with the solid black line. With some margin and increasing separation to match the penumbra's 5-minute oscillation. However, for ALMA, we do not observe such a 5-minute oscillation, or is rather quite weak. So in order to study this oscillation power, we applied a Fourier analysis to the ALMA test and to calculate the mean power for each frequency bin using all the pixels in the 3 regions, umbra, penumbra, and quiescent, to create the average power spectrum of ALMA data for each region. And the result is showing on the right figure. So here on the top left one, you can see the blue line marks the boundary of umbra, penumbra, and quiescent. And this right contours is actually the strong 3-minute oscillation region, which is integration of the two closest spins near the 3-minute oscillation frequency. So to fit this power law, we combine the two power law function seen in this term. So this tell the fitting starting from the frequency beam immediately after the 3-minute range. And also this can be, the index can be shown here, found here in these three panels. So I want to point out, we have this one as a peak in this umbrella. However, we didn't find any peak of the 5-minute oscillation in this penumbra. So it's kind of match the observation we have in this time distance plot that the 5-minute penumbra oscillation is quite weak and maybe not peaked by the ALMA. So after that, we want to study the phase relations among this ALMA band 3 and the GST H alpha subbands. So basically, we plot a light curve of these wavelengths from 1 pixel in a region of high oscillation power, that's in the red contour, and perform epoch analysis where the individual oscillations are overlaid in terms of this phase relation to the peak of H alpha far blue wave. So the left column shows that the oscillation in T2 are highly coherent for both ALMA and the BBSO. That's the top left panel. And we also overlay the curves from all the time blocks, and it shows that this general pattern persists for all the oscillations, and there's a phase shift in timing of the oscillations at different wavelengths.
3 minutes.
Okay, so let me go quickly. So in that case, we want to study this oscillation by using the RH code simulation to synthesize the chromospheric radiation in one-dimensional with FLL sunspot model as the input. The result can be found here. So let me show this movie. So basically, to understand the influence of the oscillation, we use the first complete oscillation in the T2 to fit a dynamic H alpha line profile. And you can see it matched quickly for the ALMA temperature variation with the line width of H alpha, which basically related with the temperature in that particular height. We also test a model in which a 3-minute oscillation can be explained by the cruise wave propagating upward. So this figure shows the observation at the top and the simulation at the bottom. In this case, I actually generate a several perturbed model, assuming there's a Gaussian impulse at 300 kilometers in this model, and put that perturbed model into RH code to see what we can find from this temperature profile purely from simulation. And it appears to be that this observation quite match with the perturbed model in this output of H alpha subband as well as the ALMA temperature. That's the black solid line. I also want to point out this delta T in the observation of ALMA actually serve as a quite nice restriction for the model to compare its temperature variation. So basically, in conclusion, the ALMA observer provide a unique measurement of the chromospherical temperature variation tied to electron temperature via free emission, and is relatively insensitive to atomic abundance under local equilibrium conditions. And using Fourier analysis, we studied the power spectrum of ALMA, and we discovered a phase relation and successfully test a possible physical model for the impulse driving acoustic wave propagating in a gravitationally stratified medium. And the important point is that this observation shows the power of ALMA millimeter wave observation for providing entirely new diagnostic of the solar atmosphere, and the capability of ALMA solar observations, such as a higher spatial resolution, polarization and additional frequency band that provide diagnostic at both lower and higher heights are all offer great promise for the investigations in the near future. Okay, that's the end of my presentation. Thank you.
Thank you very much for this overview on the sun. So there are millions and millions of stars in the sky, but only one sun, and it's a really unique science. So
yes,
some question in the chat.
Yeah, thank you also from my side. It's always cool to see these kind of sun movies. It's like things changing on second scales is just always impressive in astronomy, I find. So there's one question why the two-component power law fitting was adopted instead of just one, so one component.
Well, this feature, right? So because you can immediately see that this tail are different from what this the frequency, the power spectrum immediately after 3-minute oscillation, and this tail are mostly believed to kind of like a noisy part. So in that sense, we only want to find the index just after this 3-minute oscillation, and it is believed to related with the energy distribution of the turbulence.
Okay, and then there's a second question why your ALMA observations didn't target the center of the sunspot.
Well, that's because it's the solar commission campaign. So it's the target is just for the testing of the data.
So
and it's good because the testing data also shows a quite promising scientific result.
So was that field set beforehand and you were lucky that there was a sunspot, or?
I think it's specifically targeted the west part of the sunspot. So it's captured some of the quiet sun as well as the umbral penumbral region.
I see, thank you. There are no further questions.
Maybe I have one. What is the most interesting part, the quiet sun or the part in the central of the sunspot?
For my case, I would say the umbral and the penumbral case are most interesting. However, there are some statistical study regarding the quiet sun object.
Do we also fully understand the quiet sun, or?
Well, we don't have a lot of phenomenon going on the quiet sun. So basically, the important part is more or less related with a sunspot, or let's say the limb part of the sun. But the later one is a little bit difficult to calibration. So yeah, we are actually working on that part.
Maybe is there any more question? Maybe or can we learn something from other stars that will help us to understand the sun, or is it the other way around? Or because the sun is so close.
So because sun is a typical G-type star. So yeah, and maybe we can. Maybe this model, the solar atmospheric model, can be, used in other stars, and that may be an interesting part to, just simulate what we can see from other stars based on what we already quite well studied the sun. Yeah.
Okay, thank you very much. So now we are going to move to the next speaker.